Welcome to MEI Mechanics. We're on the topic of work, energy in Power 1, work and energy, and this is video 1.3, the work energy principle. So what we're going to do to start with is we're going to essentially derive this. So again, this isn't something that you'll necessarily need to do yourself in exams or anything, but it is, I think, important to have seen it so you understand where this idea comes from. So we're thinking about a very general example now. So we've got a body of mass m. It's being propelled by a force F, constant force F, and that's happening in a straight line. And so of course that will cause it to accelerate uniformly. And so if we say the initial velocity is u, and then the final velocity is v sometime later, and that's taking place over a distance of s meters. Okay, so it's just a very general situation, like a lot of the ones that we've seen so far in this course. What's going to happen? Well, we'll ignore any resistances, so we'll assume that F is the only force which is acting. Can we find a relationship between the work done, which is an idea that we've just recently been introduced to, and the change in the kinetic energy? So, what do we know about this situation? Well, we know Newton's laws. They tell us that F equals ma, where a is the acceleration. We also know that v squared equals u squared plus 2as. That's one of our Suvat equations. We know that's valid because we've got constant acceleration. So if we take F equals ma, we can rearrange that to say a equals F over m. And so we can replace a with F over m. And that's what has been done there. We'll take that equation and write it again on a new page, so that's just what we had before. And then all we're going to do is multiply through by a half m. So by multiplying through by half m, we've got something here that looks like something familiar, the half mv squared, which is the kinetic energy. That'll be a half mu squared plus fs. That m is just cancelling that m there, and the half is cancelling the 2. Then if I rearrange that, I can say fs is a half mv squared minus a half mu squared. So we've got the initial kinetic energy, we've got the final kinetic energy. What is fs? Well, fs, force times the distance travelled in the direction of that force, that's the work done. So what we can conclude then is that the work that is done by the force which is acting on the object is the same as the change in the kinetic energy. Alright, and this is called the work energy principle. It will be more complicated if potential energy is involved as well, but for the time being we're just dealing with kinetic energy, so the work done is equal to the change in the kinetic energy. And we'll, as you'll see in a few examples now, it's possible to apply that to situations and help us answer questions. So here's a simple example. Then we've got a horizontal force of magnitude 4 newtons, and that's pulling a particle a distance 5.5 meters across a horizontal floor. And we want to find the gain in the kinetic energy of the particle. We'll have to assume here, of course, that it's a smooth floor. But as long as we do that, then that means that the work that is done, remember that's force times distance, so 4 newtons times 5.5 meters is 22 joules. So 22 joules of energy is being transferred into the object, and that has to, because energy is conserved and the work energy principle tells us that that will become kinetic energy. So the kinetic energy of the particle after this has happened, or at least the gain in the kinetic energy, is 22 joules. Here's another example. We've got a ball of mass 5 kilograms, goes down a rough floor. Note that is rough this time, at a speed of 4 meters per second. And because the floor is rough, the ball is going to slow down as it moves across the floor, and it will come to rest. So suppose it comes to rest at 0.4 meters away from where it started. Well, firstly, can we find the change in the kinetic energy of the ball? Well, remember that when something's at rest, its kinetic energy is zero. So really, all we need to do is work out what its kinetic energy is at the start. We're told it's got a speed of 4 meters per second, a mass of 5 kilograms. So its initial kinetic energy is 40 joules. Because it comes to rest, its final kinetic energy is 0 joules, and so the change is minus 40 joules. In other words, it's lost 40 joules of kinetic energy in that process. Okay, so that's part 1 done. And part 2 says write down the work done by the friction. Now again, this is where we can apply the work energy principle. Alright, so that change in the kinetic energy is a result of work either being done on the object, or the work being done by that object on something else. Or if we want to think about it strictly as a work being done on the object, because it's a negative number, then that means that it's a negative amount of work. Okay, so we've got a negative amount of work done, so we've got minus 40 joules, and that's done by the friction, because that's the only force which is acting horizontally on the object in this situation. And then I think this is where it becomes really powerful, this idea that we can actually now use this to calculate the frictional force itself. We know how much energy has been lost, so we know how much work has been done, that was minus 40 joules, and we know the distance over which this has taken place. So if we assume that this force is constant, and that is a very common modelling assumption when you're dealing with friction, then the work done is minus 40 joules, and so if we take the negative of the size of the frictional force, because that force is acting in the opposite direction to the motion, so we should think of this as being a negative value, multiply that by the distance, so essentially what force times distance is equal to work, we find that that force is equal to 10 newtons. So that concludes video 1.3, the work energy principle. The next video will be 1.4, potential energy.